Hi guys, I'm back with part 2 of my Phoenix PCB Arcade Repair video series, and we are actually going to jump right into the repair in a second. Just a few preliminary words. If you didn't watch part 1 of this video, I highly recommend that you do so. I linked it in the description down below. In the last video we already fixed one PCB of Phoenix, which was this PCB stack right here. In the meantime I cleaned it and I put some feet and spacers on and finished it up really. We also looked into another CPU board of Phoenix which had several faults and which we tracked down systematically using the schematics and logic probe. We replaced 3 TTL chips, and in the end this PCB was also working. And what we are going to be looking at in this video is this logic PCB, which we will connect with this working CPU PCB, and we will try to get a complete working set out of this. Okay, before we start and get right into the repair, let me take a second and thank you all very much for the nice comments. And thank you also goes out to all the new subscribers that I got on my last repair video. I'm actually reaching the magic number of 1000 subscribers, hopefully very soon. So if you haven't subscribed yet and you would like to support the channel, please feel free to subscribe right now. And as always, if you have any questions regarding the repair, just post a comment down below the video and I will be happy to help if I can. Also, if you watched part 1, you know there's also some more PCBs waiting to be fixed. Those 2 boards are Pleiades PCBs, which is also a game which is similar to Phoenix. They will be upcoming in the next videos. But okay, right now let's just start with this Phoenix logic board. Okay, so looking at the PCB, first thing as always is the visual inspection. What can we tell? We can already tell that this is missing some chips over here. These are white sockets which look like sockets for EPROM chips actually. And well, just by looking at the schematics which I have here, we can tell that the chips that are missing are those 8 EPROM chips. And those EPROM chips are of the type 2716, which means that it is 2 kilobyte EPROMs or 16 kilobit EPROMs. That's a 16 in the name of the IC. So in total we have 8 by 2 kilobyte. We have 16 kilobytes of EPROM space in those chips. And what are those EPROMs used for in this game? Well, you can actually quite easily tell by the way that they are hooked up to the rest of the circuit, because the EPROM chips are being addressed plainly through the address bus. Each EPROM has its own select line. There's 8 select lines up here, and the output of the EPROMs, the data, is going through this buffer here and is connected to the data bus. So these are EPROM chips that the CPU can directly talk to, or that the CPU can directly acquire data from. So this is most probably program code. There are other EPROMs on the PCB, and that pretty much goes for all arcade games. Those 8 EPROMs are missing. 4 EPROMs are not missing. They seem to have been burned maybe at some point. Somebody labeled these by hand, so they probably not original. But those 4 EPROMs are also, of course, you can find them in the schematics, for instance, over here. Those EPROMs, they are not really being addressed by the CPU. They are being addressed by RAM chips. You can see them here. Those are RAM chips. And the data doesn't really go to the data bus of the CPU, but from the data of these EPROMs, some video signals are being generated. So these are probably EPROMs that contain some sort of graphical data, or that contain basically the graphics of the game, the character set and the items that you're seeing on the screen, how they look like. And well, yeah, you can just tell by the way that those chips are hooked up. The CPU has no way to actually check what is inside these EPROMs. There's no data connection to these EPROMs. So the CPU doesn't get any data directly from them, and the CPU can't even tell if they are there or what kind of data they are holding. Nothing to do with the CPU, but these are different. Those are the program EPROMs. On the web, I actually got some replacement EPROMs, which we will burn with my EPROM burner, which we'll program in a minute. One thing I have to note here is that these unfortunately aren't really 2716 EPROMs, but these are 2732 EPROMs. So these EPROMs are actually double the size of the EPROMs that are required for this PCB. But unfortunately, nowhere on the web I could actually find some 2716 EPROMs. They were only produced in the late 70s, I think. So they are getting kind of rare. But it's not too much of a problem. These bigger EPROM chips actually have about the same pin layout as the 2716s have. One difference is the 2716, to address the 2 kilobytes of data, the chip has 11 address lines, so A0 to A10. And these chips actually have 1 address line more because they have double the space. So it is A0 to A11 actually. So there's 1 pin on this IC which is A11, which does not exist on the 2716. And usually on those PCBs, those pins aren't of course used, and they are normally pulled low or pulled high all the time. They are rarely left floating. I didn't actually check what is the case with this PCB, but you can do one very nice trick to actually make this quite irrelevant. You can take the data that you would normally have on the, for instance, on the first chip here, and you can double it. So you can take the data block, you can double it, you take the same data, which is 16 kilobits, and you put the same data behind it, another 16 kilobits, so you get 32 kilobits, and then you burn this on this EPROM chip. So you got the information that the chip holds, the 2716, you got it twice on the 2732. First block, second block. So, and no matter what the highest address line is being pulled to, if it's low or if it's high, if it's low, the chip will actually output the lower block of data. If it's high, it will output the higher block, but that doesn't matter because they are both the same. So if you have an EPROM which is pin compatible and which is maybe double the size, you just put the data 2 times on this chip. Or if you even if you got 2764, I don't know if that would be pin compatible, but in theory you could actually put the data 4 times on the chip and then just ignore the upper 2 address lines. So very neat trick. So we can use these EPROMs with no problem. Okay, but finishing our inspection here, one thing that is different on this Logic PCB compared to the other one that we already repaired, the RAM chips on this PCB are all socketed. And actually there's different makes and brands of RAM chips on this board, so I think they have been exchanged, maybe some of them. Can't really tell. And also these sockets for the RAM chips aren't really factory, so somebody did some soldering here and put the sockets in. That is what you can tell. And also there are two other spots on the PCB which don't seem to have the original soldering. The ICs lack, so two of the Logic ICs, I think that guy over here and this guy over here have actually been replaced before. So it will be very interesting to see what happens when we place the freshly burned EPROMs on here, whether this will run or if we will run into some more problems. There's actually a sticker on the board which mentions bad frozen game. Well, let's just burn a fresh set of ROMs and see what we get. Okay, so I got the first EPROM file ready. I took this file just from the MAMES collection and you can see that the file actually begins with 4 times a 0 and then 31FF and so on. This is address 0, and as I told you, I doubled the data, so at the address of 7FF, that would actually be the end of the 2716 EPROM. So the end would actually be right here. After the FFFF, and in the next line you can see that I doubled the data. So this is just as in the beginning of the file. There's 8 times 0, 0 and then 31FF and so on. So this is the point where the data starts again, and the complete set of data is repeated. And this continues until FFF actually right here, and that is the end of the data on the IC. Okay, so I burned all the EPROMs and already did put them in into the PCB, hooked it up to our logic board that we repaired in the last video. So this one should be working fine. So yes, I already hooked it up right here, so let's go for a test. Okay, very interesting. So let me just put the sound out. Okay, so what we seem to get is garbage on the screen. So the game is actually not running really. So there still must be some fault on the Logic PCB. I'm actually kind of happy about that, because now we can start with our troubleshooting again. And it would have been a rather disappointing video maybe if it was just replacing the EPROM. So, well, let's get into the schematics. I will take out my logic probe and we will try to find the problem as usual. Okay, well, as always, the magic question now comes up. Where do we start? Where do we start our troubleshooting? What parts are we actually looking at? What tools do we need to use? And I think we can just, for a start, we can just get back to the basics. We know that the CPU PCB is working, because it is working with the other logic board. And we have garbage on the screen, so the clock signal and the horizontal and vertical counters and everything else that is coming from the logic PCB actually appears to be working also. We get garbage on the screen, which means that the CPU isn't actually executing the program like it is supposed to, but at least the logic PCB is with its parts of the video output circuitry is able to produce this garbage on the screen. So we pretty much have to figure out why the CPU isn't executing the program at the moment. And there's generally three kinds of problems that could be the cause for this, I would say, and we can already exclude two categories of problems. First problem would be a problem with the CPU itself, or the signals that the CPU actually needs to run, like a clock signal, reset signal, etc., etc. We can exclude that because we know this PCB is actually working with a different logic board, so the CPU itself can't really be at fault. Second problem category we can exclude really is, at least if we did everything correct, but the EPROMs itself themselves could be the problem if they were defective, which sometimes happens on arcade games, of course. But these are freshly burned, so I think we have to exclude them also as cause for this issue. So the third category of problems is really coming up as very probable cause for the issue, and that is that there's most likely a connection problem between the CPU and the EPROMs, which leads to the CPU not really getting the program code out of the EPROMs. And that in itself can have several reasons. Maybe I can show you more about that while looking at the schematics. Okay, so looking at the schematics for the CPU PCB, we can see the CPU over here, and there are signal lines coming from the CPU, which are the address lines. They are labeled A0 to A10, and those 11 EPROM, these 11 address lines are going to the EPROMs. They are originating not directly from the CPU, but they're coming out of those chips here. Those are latches actually. They are not really in question because this CPU PCB as a whole is working. Those signal lines are going through the connectors on the side of the PCB, and they are going over to the logic PCB. They are entering the logic PCB right here, A0 to A10, and they are directly, without any more chips or anything, they are directly feeding into the 8 EPROMs. So we could start by actually checking if all of these address lines are really connected to the EPROMs. Okay, so one way to do this is actually set up this some kind of lookup table like I did right here. So I have all the address lines, and we need to actually see if there's a positive connection between IC2 on the CPU board, which is this guy over here from who the address lines are originating. And we can just check if they are getting through to the EPROM. I just selected this first EPROM right here. So I made this table line number 2 from IC2 on the CPU board has to be connected to pin 8 of the EPROM. So I already hooked this up to pin 8. I have the other end of the probe here. I'm just doing a continuity test. So if we are looking at IC number 2 and checking pin 2, yeah, this is IC2. We can see that there's continuity, and I actually went to all of the through all of the address lines from A0 to A10, and they all have positive continuity. Okay, so the next thing I actually checked was the data bus, and we can see the 8 data lines here coming from IC number 1, and all the pins are labeled here, and they are going over to the logic PCB. They are not directly connected to the EPROMs, but they are connected through this buffer actually. So the output of the EPROMs can be activated and deactivated, so to speak. So I want to test the connection between the CPU PCB IC1 and this buffer chip over here. So I made another table for all the data lines, DA0 to DA7. And I listed all the pins so I can do a continuity check for those. Okay, and as it turns out, they are actually all connected. So we have the address and the data connection to the buffer, which is working. The next thing we could check would be if the EPROMs are actually being enabled. So if the CPU wants to talk to the EPROMs, it needs to send a chip enable signal to each of the ICs. And for these EPROMs, this would be on pin 20, which is 24, 23, 22, 21, 20, which is this pin over here. And we see we have an intermittent signal, so the EPROMs are actually being being selected intermittently. So these lines seem to be also working. So it is now really getting more and more interesting. So by looking at the address lines, data lines, and chip enable lines, what we now excluded is actually a connection problem. A connection problem is not the reason why those two instances can't talk to each other. They are wired together as they are supposed to, judging by the schematics. So no problems there. We excluded actually, by looking at all this stuff, we actually excluded some problems with, for instance, with the connectors, with the cables between the PCBs, and also damage traces or corrosion in the sockets or whatever. If the connections are fine, then all these things are excluded. So we need to think more about the topic and find a different reason why, even if the connections are established, why there could be a communication problem between the two. What I think is very likely at this point is, after checking all this, that there's a problem with the buses, really. So there's a bus problem or a bus conflict going on. Regarding the address lines, I think the address lines may be not too suspicious. The address lines are driven by the CPU itself, and they are going directly to the EPROMs, and nobody really else is changing the address lines. But with the data bus, it's a little different. If the CPU wants to talk to any other or to any instance on the board, like for instance, it wants to talk like to this third EPROM here, or it would like to talk to the RAM chips over here, or it wants to check on the dip switch settings, or it wants to talk to the sound circuit. It will always set an address. You can think of that address as like a telephone number, for instance. So each of these places, each EPROM chip and everything has their own address, their own telephone number. So it selects this address, and then it's actually activating this instance over some sort of chip-enabled signal, which is working over here, as we saw. And then, for instance, if it wants to retrieve data from the EPROMs, the data is then being output through the data lines, and it is going back to the CPU. And this could be a place where the problem is, because the data lines are really driven potentially by rather a lot of ICs on the PCB, because there's a lot of instances or chips on the PCB that are able generally to modify and talk on the data bus. Normally they should be all switched off if they aren't addressed, but that could be really a problem, that any of the guys that is communicating on the data bus is maybe messing up the communication. So I would suggest that we actually check what kind of instances we are working with here on the logic PCB, and we should actually check what are the instances that are hooked up to the data bus. And we could actually look into the multiplexers and latches that are actually connecting those instances to the bus and see if they are okay. That, I think, would be the next step to do. Okay, and looking into this in detail, we actually have 4 instances on the logic board where a certain circuit is able to talk on the data bus, and one instance is of course the EPROMs, and the data bus is up here and is going down here. Those guys are connected to the data bus through this IC, which is IC 37. So looking at the PCB, we have the EPROMs here, and IC 37 is this guy over here. So they are connected address-wise directly to the CPU and data-wise through this IC. Then we have some kind of dual architecture here going on. This looks very similar. 2 instances of RAM, which should be video RAM, both of them, connected to some EPROMs for graphical data. So maybe one is background, one is sprites. I don't really know, and it's not necessary to know, I think, at the moment. They both have their ICs. One is this guy over here, IC 38, and this guy over here, 22, which are connecting them to the data bus, because the CPU needs data bus connection to the RAMs if it wants to write or read from the RAMs. This is where the data goes that is stored on the RAMs, or that is read from them. So looking at the board, we see the dual architecture also here. So this is 4 RAM chips with 2 EPROMs, and this is IC 36, which is connecting those guys to the data bus. And second row is here, 2 EPROMs, 4 RAM chips, and we have IC 22, which is connecting those guys to the data bus. And we have a fourth instance down here, which is also connected to some RAM up here, which is IC8, which we have down here, which is also potentially able to talk on the data bus. So we will maybe, so we got this guy here for the EPROMs, those two guys for the RAMs, and this other guy also for the RAMs, and we will actually probe those 4 chips and look if we see anything interesting. Okay, so starting with IC 37, looking at the EPROM chips, we can actually see that on all address and data lines there's activity going on. So at the moment the address lines are being driven by the CPU, and the EPROM chips are actually outputting data, which is unfortunately still not leading to the game working, but this is pretty much a good sign that there's actually some data activity going on, and the data is also reaching IC 37, and well, I already probed this chip. Is like on every single pin there's something going on here. So what we can say is that at the moment on both sides of this IC there is regular activity on all the lines. This IC again is used to connect or disconnect the EPROM chips from the data bus, so they are enabled or allowed to talk on the data bus, or they are not allowed to talk. So we could actually look at pins 1 and 19 of this IC to check what is going on there. So pin 19 is an intermittent signal, and pin 1 also. So the CPU seems to be allowing intermittently the EPROMs to talk through these lines to the bus, as it seems, because this enabled signal is also intermittently on, which would very likely be the case in regular operation. So we don't see any real problem with this IC at the moment. Okay, and one more interesting thing I just tried, I actually removed the CPU from its socket. Doesn't really make much difference for the display, but if you probe the chip now, you can see that well, about half of the legs are high and the other half is still doing something and toggling. That is because on the EPROM side of the chip there is no activity at the moment. All signals are high, and the data bus still has activity. So somebody is talking on the data bus here on this PCB at the moment, even without a CPU in place. That can actually be correct, because maybe without a CPU, the chip-enabled signals aren't really regulated that well, I would presume, and maybe the RAM chips are outputting their garbage on the data bus, because they are not only driven by address lines, but also by the horizontal and vertical screen position and so on. So this would actually be plausible. But we can see, so there's no activity on the EPROM lines if the CPU is being removed. EPROMs are silent. Actually, there's still something going on the data bus, and the enabled signals are switched off. So yeah, well, no indication of a malfunction here. Okay, I just found something real interesting with these RAM instances here. Well, first of all, if we look at those buffers that are connecting the RAMs to the data bus, we can see there's activity pretty much going on again on both sides of this IC. So the RAMs are talking and the data bus is active also. You can see that they are actually not the chip enabled signal is high, which means that this chip is not enabled. So this chip and also that chip over here, pin 19 and pin 1, they are both high. So those two chips at the moment, they should not be connecting the RAMs to the data bus. That is what you can see here, and there's activity on both sides. Okay, now let me show you something real interesting. Okay, what I did now is I removed those 4 RAM chips from their socket, and now when probing the buffer, we can see that the RAM chips, they aren't really talking anymore, but that is what we see on this side here. The bus is still active and still doing its thing. So this is what we would expect. So we removed the RAM chips. The RAM chips were the guys that were talking to this IC here. Now they are silent because they are gone, really. And the bus isn't really affected by that because the connection was switched off anyway. So the RAM chips weren't supposed to be talking on the bus anyway. So, well, this is what we actually would expect. But the very interesting part is coming now. Okay, now is the part where it gets real interesting. I removed those other 4 RAM chips here, and their buffer chip is this one right here, IC22. And what we would expect, just with like with this RAM bank, is that we have activity on the data lines maybe, but of course not on this side of the buffer where the RAMs are connected to, because the RAMs are removed, right? So we are checking at IC22 and we see there's some intermittent signal going on here, and also on the on the data bus side there's still intermittent signals, but also on the other side where the RAM chips are situated. So, and this doesn't make really much sense, because how can here be an intermittent signal if the RAM chips are actually removed? So how can anyone talk on this side of the buffer if there is no one actually there that can output some intermittent signals? So what we have to conclude is actually that this buffer actually is very likely to be defective and to be specific, to be defective in a way where he actually puts the signal permanently, the data bus signal permanently through to those RAM chips. So the signals that we're seeing on this RAM side are actually probably just the data bus. And when we look at the pins again on the chip select pins 1 and 19, we see that they are both high. So this chip shouldn't be actually doing anything, but it is doing something. It is connecting the data bus to those RAM sockets, so to say. And that is incorrect. So maybe this chip is actually permanently connecting those RAM chips to the data bus. And if that was the case, then this would explain why the CPU can't talk to the EPROMs. Because, you know, the CPU is addressing the EPROMs and wants to talk to them, is enabling them, and those EPROMs want to talk then to the CPU back through the data lines. But those RAM chips over here, they are connected to the data lines also, and they are connected all the time. So if they are talking, and they are talking permanently, as it seems, you can see this in the other bank, then they are talking all the time on the data bus. So the data bus will, as a result, will be all gibberish, because when this guy wants to say something, he's talking all the time. And the CPU can't really understand what this guy is saying. This is how you might put it. So I think this is a really good theory, and I think we should actually go ahead and remove this multiplexer IC22. Okay, I just removed this IC from the PCB, and I wanted to show you something which is really nice. If you look at the monitor and I turn it on, you can see it says phonix, and there's score, high score, and then the game is actually crashing, but we are seeing signs of life. So the game is actually running, and it's of course not working because half of the RAMs are missing, because this chip is not in place, and this is probably the reason why this is crashing. But just by seeing this phonix label on the screen, we can already tell that now the CPU must be able to talk to the EPROM chips really, and actually get to the program data. So now the CPU is running all right. This is a very good sign, and it appears to be really the case that this guy, when we removed it from the data bus, we stopped the crosstalk, so to say, that this guy was causing, by letting everything just go straight through, no matter what the chip select signal was. And yeah, so we stopped this crosstalk by taking this guy out, and we got the first signs of the game back. Just great. Okay, from our trusty parts PCB, I removed IC number 1, which was in 74LS245, which is the one that I removed here. It's looking kind of old-fashioned, really, but well, I already hooked the game back up, and now check this. So what do you say? The game is working, I would say, as it appears. Let's check. Looks fine. So great. Very nice. So we got our second phonix PCB board set running. Great success. Replaced the EPROMs, replaced this IC over here, and this logic board was working again. I think actually I mentioned before that there were some marks of soldering activity on the solder side of this board. So somebody socketed those RAMs, somebody actually looked at this IC and removed it at some point, which is one of the data lines buffers, and another IC has been removed, which I think was this guy over here, which has to do with the address lines going to the RAM. So I think somebody already was getting really close to spotting the problem, but he somehow missed the final lead. Well, this guy over here was the culprit. This board is working again, and I hope, really hope that my explanations haven't been too confusing. Somehow I'm actually in doubt sometimes that people can actually quite follow what I'm trying to say, because I don't know if I'm really able to express myself well enough. But all that counts at the end is that the PCB is working again. And yeah, well, again, thank you very much for watching. If you haven't subscribed, please do so. Looking really forward to 1,000 subscribers. And of course, you can look forward to seeing my next videos, which will probably have to do with the rest of the PCBs here, which is 2 copies of Pleiades, which are missing some ICs, chips, and which are incomplete and which are not running now. So we'll have to fix those as well. So, and in the meantime, have some fun and see you in the next vid. Bye bye.